All right, folks, it's Bass Action, back in action here. In this video, we are going to look at solving quadratic inequalities. And you can see up here in example 1 that we're going to look at 2 different methods. And it doesn't matter to me which method that you choose. I tend to gravitate towards one of them, but you can choose whichever one you would prefer. So they both start off the same. So you'll notice that here I've given you some space here to solve this inequality. Now, I do want to point out that when you are solving an inequality and you're reading an inequality, you always need to start from the side of the variables. So in this case, we're trying to find where this quadratic is greater than or equal to 0. If all of this were on the right-hand side and we were reading from this direction, we would want to know where the inequality was less than 0. So be very careful with that if your inequalities and your variables are on the other side. So the first thing that we're going to do to solve this, we're solving for x, and we all should be able to easily recognize that this particular quadratic factors nicely. That was certainly intentional here, so we're going to have an x plus 2 and an x minus 6, and an x plus 2 greater than or equal to 0. So we would see that we're going to end up with 2 values for x, and it's going to be 6 and negative 2. Now, using that x equals 6 and negative 2, this is not our actual solution. We're going to use these in both of these methods. Okay, so both methods are going to use these 2 x-intercepts. So the first method is to just sketch a quick graph. So we're going to make a nice just x-axis. We don't care about the y-axis here. We're going to put our 6 and our negative 2 on here. Negative 2 and our 6, okay? So we're going to put our 2 numbers on there. And then we're going to recognize that this quadratic opens up. We can tell that because the leading coefficient is positive, so it's an upward turning parabola that's going to cross the x-axis at these 2 values. So I'm just going to sketch in this rough parabola here. We don't know what it looks like, and it really doesn't matter. All we need to know is where it's crossing. Now, since this inequality is going to be a greater than or equal to, I'm going to put some nice solid dots here at the intercepts because I do want where it equals 0. And then in particular, I want to know where this quadratic is more than 0. In other words, where are the y values more than 0? And those y values are going to be out here and out here because we can see it's above the x-axis and above the x-axis. So our solution for this could be negative infinity to a negative 2, bracket, union, bracket, 6, positive infinity, and of course the parentheses on those infinities. Now, the second option would be to take those same values for the x-intercepts, and we're going to put those on our number line again. So the 2 methods start off exactly the same. So negative 2 and 6, just like before, because it's inclusive, we're going to put some nice solid circles on those intercepts. And now we're going to actually test some intervals, okay? So we're going to pick some values from each of the intervals and determine whether or not we get a true statement. So if I, for example, from this interval right here, I'm going to choose x equals a negative 3. And if I choose that negative 3 and I substitute it into either portion, it can either be the factored form or the non-factored form, I'm going to substitute that in, and I'm trying to determine whether or not it's going to be greater than or equal to 0. Since I only need to know whether it's positive or negative, I don't need its actual value, okay? So when I put a negative 3 into this factor right here, I'm going to get a negative value, some negative value. And then when I put my negative 3 into this value right here, this factor right here, I'm going to get another negative value. Oops, didn't mean to write that one there. I'm going to get another negative value. And of course, a negative times a negative is in fact greater than or equal to 0, so this interval gets kept. The next thing that I would do is I would test the next interval, and I would pick x equals 0 because 0 falls in that, and that's going to be the easiest. Now, when I have an x equals 0, this form of the quadratic is the easiest, and I can see that, oh, at x equals 0, I have a negative 12. And when I'm trying to figure out if negative 12 is greater than or equal to 0, it's not. Negative 12 is less than 0. So this one does not work, so we're going to throw that interval out. Then we're going to test again. And this time I'm going to choose x equals 7. Again, if I'm testing, I like to put it into the factors. I'm going to get a nice positive value in the first factor. I'm going to get a positive value in the second factor. Positive times positive is in fact greater than or equal to 0. So again, I'm going to keep these two sets. And again, my solution is negative infinity to negative 2 with a bracket, union, bracket, 6 to positive infinity. Same answer, no matter which method I use. So you can choose whichever one you want. It really doesn't matter. So just wherever you feel comfortable. Now, using this solution, what we should be able to recognize is that if I change the inequality sign, if I change it to just a greater than, my solution should stay exactly the same, but now instead of brackets, I'm going to use parentheses. So a negative infinity to a negative 2, parentheses now, union parentheses, 6 to positive infinity. So it's these parentheses that are going to change. If it was less than or equal to 0, now we're going to choose a different portion of the problem. We're going to now choose this section right here when we're looking at this less than. And since it's inclusive, we are going to, in fact, include those ends. So we'll say a negative 2 to a 6. And then if we just drop the inclusive, we're going to write it as a negative 2 to 6 with parentheses, okay? Now, another scenario that we could potentially look at would be solving something graphically. So sometimes you'll be given a particular graph and you need to choose it. So we're going to go ahead and we're going to graph these two very quickly. Now, these should be pretty easy functions for us to graph. So we're going to do our upward turning parabola that's been shifted down 4. So I'm going to move that down 4, and I can certainly find these x-intercepts mentally pretty easy here at plus and minus 0. So I'm going to sketch that in. I could even probably take that 3 and come up here and give myself a nice 9 to give myself a little better shape. Negative 3. Actually, I didn't mean a 9 on that. My brain was, need to move that down. Silly me, I was forgetting that it was shifted there. How about 9 minus 5 is going to be, or 9 minus 4 is going to give us a 5. So let's put that point in there. That's okay. So 3, 5, that'll give us, again, just a little bit better shape when we're trying to solve this graphically. Negative 3 up 5. We'll ignore that 9 that's up there, although it's going to actually get reasonably close when we sketch this in. And then my negative sloping line, that's going to have a y-intercept of 2. So up 1 over 2, up 1 over 2. Go. It's really up 1 over 1. My brain was saying 2, but I was actually moving 1. All right, so there we go. We've got a rough picture of this. Now, if we're solving this graphically, our solution, what we're going to do is we're going to find where these intersect here and here. Okay, we're going to find where these intersect, and then our solution is going to be the values that are going to be between those, in between those 2 points. So when we write this solution here, it's going to be from a negative 3, to a 2. And it's going to be parentheses because this was not inclusive. Because what we're looking for is where is the parabola below or less than the line, and here's where our parabola is below. If that was flipped, we would be choosing these outer portions. Now, sometimes the graphs can be difficult to work with, especially if you have the ability to draw on the graph. So we can look at how we would solve this algebraically. And if we did this algebraically, we would take our x squared minus 4 less than our negative x plus 2. And solving algebraically says we would need to move everything over to one side. X squared plus an x minus a 6 less than 0. And then we would choose a method from up above. So we're going to definitely have to factor this. So x plus 3, x minus 2 less than or equal to 0. I personally like the graphing method. So I would look at this and say, hey, I have an upward turning parabola that's crossing at a -3 and a +2. And I would sketch in that little parabola. I want to know where it is less than 0, so my solution would be this portion right here, because that's where it's less than 0. And sure enough, I get the exact same answer, okay, as I did looking at the two graphs together on the grid. Now, the last one I want to include is because this is a very commonly missed question. If we are trying to find where they're equal, we're doing the same thing algebraically that we did before. We're doing our x squared minus 4 equals our -x plus 2, and just like before, we're shoving everything over to the one side. Kind of struggling on my writing here today. And then I'm going to have an x plus 3 and an x minus 2. And our answer is x equals a -3, comma 2. What I really want to emphasize here is that this is not an ordered pair. Okay, this is not an ordered pair. We do not give these 2 points right here as the solutions for this equation. We just solve the equation and solve for x. We do not give these ordered pairs. The only time that we would give these 2 points is if it specifically said that it was a system of equations, okay? Other than that, we're either going to give this interval of x values for the inequalities, or we're going to give the 2 specific x values that make the true statement.